As an addendum to these exact differential equations, I thought it would give you an intuitive version of why the total differential is what it is. And so, recall we've been working with this. If z is a function of two variables, f of x, y, then the differential of z, the total differential, is the partial of f with respect to x times dx plus partial of f with respect to y dy. So I kind of figured out why this is true without producing a formal proof. And the secret is this. If we take the derivative with respect to x of a function of two variables, what's going to happen? So let me work kind of a parallel problem down here. Suppose I took the derivative with respect to x of this term, x squared y cubed minus sine, I'll make it plus, sine x plus y plus 4x minus 7y. Okay, if I was taking this derivative, I would first take the derivative of x squared and get 2x times y cubed. And then, because of the product rule, I would have 3x squared y squared times y prime. The y prime is the part we get by doing implicit differentiation. Here I have the cosine of the function times the inside. Well, it's the cosine of the function, x plus y, times the derivative of x plus y. Well, that derivative would be 1 plus y prime. And then this derivative would be 4, but that derivative would be minus 7y prime. Alright, so here's what I want you to think about. When we take this derivative, we're in effect, in one aspect of it, we're doing the partial derivative with respect to x. In other words, we're treating y as a constant. And I did that here. This partial derivative is 2x y cubed. And with respect to x. And this partial derivative with respect to x is the cosine of x plus y times 1. So, and this partial with respect to x is the ordinary derivative, 4. So we've knocked out this term and this term multiplied by the cosine and the plus 4. That is taking the derivative of x while treating y as a constant. That's precisely the partial derivative of the whole thing with respect to x. And then the next thing we do is we also take the derivative of terms with y's in them. And so in here it manifested as a product rule. And so I had plus the derivative of y cubed is 3y squared times x squared and then y prime. And so, and then this over here, this derivative with respect to x, accounting for the y, is the cosine of x plus y times 1 plus y prime. So here's the y prime. And then here's the ordinary derivative, 7y prime. So what did that tell us? This is the partial of f with respect to y times the derivative of y with respect to x. Because this variable here, x, differs from the y, in each of these cases, we had a y prime term show up, which is y prime is dy dx. And so we end up having, if you look real carefully, this is the partial of the function with respect to y. In other words, the derivative treating x as a constant, but with respect to y, and then also multiplying by the derivative of y, dy dx. So I wanted to give you kind of a specific example to see where this is shaping up, where that's shaping up. And now it's quite simple. If we multiply both sides by dx, then we have our total differential. So I'll multiply everything by dx. This cancels. I have the differential of f of xy, which is the same as dz, is the partial of f with respect to x times dx, plus, and here the dx's cancel, partial of f with respect to y dy. And there it is, the total differential. So I wanted you to see, at least sort of intuitively, why that's true. Now that's not a formal proof, and I would have to work harder to come up with a formal proof, and I'm not sure it would be all that productive at this level of mathematics. But I wanted you to see that they just didn't pull this out of a hat. It really does work.